One of the challenges that we face in civil engineering structural design is how do we connect the various structural elements, particularly how do we connect beams to columns. Now in steel construction, that's typically through some sort of a bolted or through a welded connection, or maybe even a combination of both bolts and welds. But when it's reinforced concrete, then the question is, how do you do that? Now, technically, reinforced concrete typically is always assumed to be cast in place reinforced concrete, in which case things are typically integrally connected. So that answer isn't so much how do you connect it as it is how much reinforcement do you need for moment and shear transfer through the beam to the column. But when you're talking about precast concrete, where you're making those columns and beams at a manufacturing yard or a fabrication yard, and then you're shipping them on site and assembling them a little bit like an erector set, in other ways, very much like a steel frame construction project, then how do you do that is a fairly significantly different type of question. And typically it involves some sort of steel embed plates and some welding that's going on, but you don't get typically significant moment transfer. And how do you temporarily support things while you're doing all those other kinds of details? So one of the answers that you have is to put a little ledge on the column so that you can place then the beam right on there. And that ledge is called a corbel. And because of that, though, there's some offsets that we have to deal with in terms of what happens now inside the column, and we're going to explore that a little bit in this particular example. So let me kick over here to that example, right? So an example PS 6.4, you've got on the top of the page the three-dimensional view of this column with this corbel, and then you've got that beam end that comes down and then needs to have some sort of support force or the reaction there. And of the variety of challenges that we have here that we have to deal with is that this corbel could shear right down the column face, sort of along that dashed line that you might be able to see. Or it also may want to rotate and try to pull away from the column, which is the more typical cracking that we begin to see associated with that particular kind of problem. To the point where what you do see some designers doing is taking reinforcement and going from the upper left and extending it down into the lower right into the corbel. All those dark lines you see represent the steel reinforcement. It is a particular challenge that we have to address in these precast systems, right? So we're not going to focus so much on the behavior of the corbel as we are the impact of having this reaction that is offset from the longitudinal axis or centroidal axis of the column itself. It's going to introduce bending into the column. And we're going to just look at this from a stress basis as opposed to looking at it from the design basis, which is what you would learn in the reinforced concrete design class. We have a somewhat, not just somewhat, we have a very small column that this is sized at 10" by 6". You don't see the 6" dimension in this particular image. Is the basic column cross section. That's very, very small. Even a 10" by 10" square column would be small from that kind of perspective. Right? So this is a little bit of an unusually small case. That the 30 kip reaction is not unusually small, but the rest of it is somewhat small. And so we're going to look at this offset load is eccentrically placed load and see what the stress effects are on the overall member. All right, so here we have a simple representation then of our system. There's your 30 kip load, our 10" by 6" cross section that we've got going on here. And our goal is just to find what the stress variation is on the cross section. So the first thing that let's do is actually to predict what we're going to need from a geometric properties standpoint. I mean, we know we've got an axial force that we're going to be dealing with. So we know we are going to need the cross-sectional area. That's of no surprise at all. And that's, of course, very easy. 10" by 6" or 60 square inches. No big deal there, right? What you might not as easily see is that we're going to end up with some sort of bending moment, right? And that can be more easily seen by, hey, the axial load is, of course, right here at acting effectively at the centroid. It's over here. That's going to be our axial load P, or actually maybe better said N. That's going to be, really simple. That's going to be our 30 kips. But notice there's now a force couple at work here, right? So there is a distance of 5 inches over, right, from here to here. And so that's going to leave 8 inches over for that force couple, and we're going to need a restoring moment that is associated with that. And we might generically just write that as N times E, and we'll come back and put the number on that in just a second. But that's going to tell us that we do have bending. We're going to need the second moment of area, and I attempted to call that XX. There's not really an XXYY business in the model or the drawing that we've got here, but I think we do have in the original drawing. This is the ZZ axis, YY actually is the longitudinal axis, and this I believe is the XX axis. So this would actually be IZZ, and it's just going to be our 1/12 BH cubed. And so the base here is this one, 6 inches, times the height, 10 inches cubed. Don't know why I changed the symbol for the units there, but 6 over 12 is a half. The 10 cubed is 1,000, so that's going to be 500 inches to the fourth for the I. Okay, I bet we're going to want S, which is of course I over C, and so that would be 500 inches to the fourth divided by the C going to the outer fiber, which would be 5 inches, so that would be 100 inches cubed, or the S, either direction. All right, let's look at then the resultant forces. We've actually already found them. We already know the axial force, N equals 30 kips, and the bending moment is going to be 30 kips times our 8-inch eccentricity, or 240 kip inches. All right, so now let's go find our stress variation. I always, when I do this, like to show the actual stress block, as in the stress model. Here's the bottom of the cross section, and the axial stress then is just going to be sigma equals N over A. And for us, that would be then our 30 kips divided by our 60 square inches, so it'll be pretty small. It's only 1/2 KSI. Now, that's not particularly very big. It's compression all, right? And then we've got, we'll add to that normal stress, the variation that comes from the bending. Right, now we're going to have compression, right? The arrow points to the compression side on the right. That means the other side will be tension, be 0 at the neutral axis. And the maximum here out at the outer fiber will be M over S. And so that would be our 240 kip inches divided by our 100 cubic inches. Hey, I can do this one in my head. 240 divided by 100 is 2.4 KSI at those two outer edges. And so the net variation that we're going to have is just the sum of those two, right? We're going to have a 2.4 minus a half over here at the one side. Let's get the edge of the cross section there. And if you want, let's see, that'll be tension, right? So that will be a max of, or net of 1.9, 2.4 minus the half, right? And then on the other side, we'll add the 2, so it's 2.4 plus 0.5, so 2.9. And it's just going to be a straight line variation in between those two. So the location of zero stress is actually shifted over a little bit. What we're really doing is superimposing this on top of that. This sets a new baseline for the sort of effective zero. And so it's sort of like taking this diagram and shifting it down a little bit is in effect what, or really actually taking it the other way. That depends on what you call going the other way. But there's your net that you end up with here for your stress variation for the normal stresses, with a max normal stress of 2.9 KSI and a max, that'd be compression, and max tensile normal stress of 1.9 KSI for the situation.